Is the second speaker, Professor Anne from Paris 1. She will speak on large deviation principle and inviscid hydrodynamical equations.
Thank you very much. First, I would like to, of course, thank the organizers for their invitation to this nice conference in a very prestigious place. So the results I'm going to talk about have been jointly obtained with Hakima Besai. So my talk will have three parts. I'll first describe the models. There are two models I'm going to talk about, the Navier-Stokes equation and the so-called shell models of turbulence, which are kind of toy models, but which are much better behaved. And I'll describe some random perturbation. And then in the second part, I'll formulate the LDP, the large deviation principles we can obtain, and then, of course, some job will be saved by the previous talks which were given on this topic. And if time allows, at the end of the talk, I'll give you some ideas of the proof. And the method I'm going to use is a method which has been used yesterday by Tushen Zhang concerning the weak convergence approach. All right, so let's start with Navier-Stokes equations. These are very celebrated equations. They were described on Monday by Kim Ju in the setting of three-dimensional Navier-Stokes equation. Here I'll stick with a domain in R2 for which things are better behaved. So we are describing the velocity of a fluid, and here we have some important item which is the viscosity. In the Monday's talk, the viscosity was taken to be constant because it was not being changed during the talk. While here the aim of the game will be to let the viscosity go to zero. So I do have this viscosity, which is going to be an important item. And of course I have some boundary conditions. So my bounded domain, I suppose that the divergence is zero in the domain, that the fluid is tangential to the boundary. That means that the scalar product between the velocity and the outward normal is zero. And one more very important item for what's going to happen afterwards is that the curl, which is a kind of, I'm sorry, I use the French notation, but afterwards I change it to the curl. I mean, just here to this notation, because it seems that the notation depends on the country. So anyway, this curl is going to be zero, the notation at least, on the boundary, and this curl is here. It's some kind of third component of the exterior product if you just complete your vectors in R2 as vectors in R3. All right, here I have the pressure term, which will very soon disappear because I'll project on divergence-free fields. And here there is a famous nasty part of the Navier-Stokes equation, which is a bilinear term. And for the time being, I have some external force, which can be deterministic or can be random. All right, so the space which we are going to work with, to start with, will be nice Hilbert spaces, namely those L2 integrable functions on the domain, which have null divergence in the domain and which are tangential on the boundary as well. But since we are going to have the viscosity go to zero, eventually it will be equal to zero, and therefore we'll have to introduce some to deal with some non-Hilbert Sobolev spaces, which I'm describing in here. So this is a standard Sobolev space where you are k times differentiable with q's power of integrability on the domain. And every time I'm going to intersect that, imposing these extra conditions. And as in Monday's lecture, for the time being, an important space will be H12 with the extra constraints. All right, so I have not imposed that anything being equal to zero on the boundaries, which means that eventually I will have to face some surface integrals when I'm going to take integration by parts, just looking at the Stokes operator and integrating by parts with respect to something which is in V. Some kind of surface integral is going to pop out, which is written this way. And in fact, I have some operator from V to V prime, which is not exactly the Stokes operator, well, which is a Stokes operator, but with some byproduct, which is the surface integral, which is related to what Professor Da Prato mentioned in his talk on Monday, but here in a very simple setting. That's basically the Green's formula. If you dislike it, you can add some extra conditions, and you will not going to lose much of the talk. All right, now this bilinear operator in this Navier-Stokes framework, it goes from V cross V to V. It's defined this way. It's kind of scalar product between u and the gradient of v, acting on some third element w. And it has two very important features. On one hand, it's antisymmetric if you switch both the last terms, the last items. Here you see the minus sign popping out, which means, of course, that if u3 matches u3, if u2 matches u3, you get 0. And on top of that, if you take u regular enough, then this duality relation between bu and u and au, this is equal to 0 on the domain. And this will be very important for further issues. All right, so this is a very celebrated model, but the problem, of course, is that here this bilinear operator is a bit nasty. So let me describe, as I told you, some kind of simple-minded toy model, which to some extent captures some of the features of B, but for B which is better behaved. So think for a moment in terms of eigenvalues and eigenfunctions decomposition of an element of L2, and look at the eigenfunctions, which would be UN, the eigenfunctions which are in the blue, and think of the eigen elements, UN. So if you expand an element of L2 in some orthonormal basis, you will get some kind of square integrable sequence, right? Some sequence in L2. Now here, take this sequence to be complex valued because I want that this antisymmetry with respect to the last two terms in B hold, and this will force me to deal with complex valued sequences with a standard scalar product. And here you see that's what I mentioned a moment ago. You can think that more or less you have taken some kind of eigenfunction decomposition of the Laplace operator or the Stokes operator. So Kn is a constant multiple of some sequence mu to the n, where mu is strictly larger than 0. So as previously, more or less, V is the domain of a to the 1/2, and we'll have some interpolation space, which here is a Hilbert space, which is the domain of a to the 1/4. And this makes me think that here I forgot to mention the fact that in the framework on the Navier-Stokes equation, we also have some interpolation space, which here turns out to be L to the 4th in the two-dimensional setting. All right, so now we have to describe this bilinear operator, and I'll let you enjoy the formulas. Okay, they are not very appealing, I agree. But if you look at the bottom part, it's nicer, because here you see that, I made a mistake here, it's not V. Okay, it's true, but no, it's not, no, that's not the way it should be. If it goes from this interpolation, it should be strict H, I think, here. And here you go from this interpolation space cross itself into H. And again, because of this choice, this clever choice which has been done between the elements of the sequences and their complex conjugates, you see that in both cases, this antisymmetry is going to hold. And on top of that, if you choose now these A and B coefficients in a clever way, and it turns out that the choice is exactly the same for both Goy and Sabra-Shell models, you get again the fact that B of u and AU is equal to 0. All right, now what about the random perturbation? Well, it's going to be very similar to that which was described by Kim-Ju in his talk concerning the 3D Navier-Stokes equation. On one hand, we'll have, and also, of course, also what Tusheng did something different because he had space-time white noise. Here we are in an infinite dimensional setting, so we have some WT, which is an H-valued linear process with trace class covariance operator. And as usual, we'll have the reproducing kernel Hilbert space of this noise be denoted by H0, which is q to the 1/2 times H, with a standard scalar product. And we'll look at Hilbert-Schmidt operators from H to H when we multiply S by the root of the covariance matrix, covariance operator. And this nice space will be that of our diffusion coefficients. So we'll have some diffusion coefficients which start from, which may depend on time, but very soon I'll just drop the time dependency in order to ease comprehension and notation, and which takes place into this kind of Hilbert-Schmidt operators. And of course, I have to impose some growth condition and Lipschitz condition. And here you see that there are several items on the right-hand side for both the growth and Lipschitz condition. Those in blue are related with the H norm, so that they are nice guys. and those in red are related to the V norm, and these are the bad guys. And in order to get even well-posedness and nice estimates, we'll have to lower to have small estimates in here. Well, of course, precise examples of that can be formulated the way Professor Kim Joo did on Monday. All right, so for the time being, the diffusion coefficient may depend on the gradient of the solution if we are in the framework of the Navier-Stokes equation, and it may depend upon the V norm in general setting. All right, so of course, to start with, we should have a well-posedness theorem, so that the well-posedness theorem tells us that whenever we take nu strictly larger than 0, and that's of course very important, whenever we suppose that we have a force moment of the initial condition to our problem, which is in here, and of course in the right-hand side now the forcing term is going to be the multiple of this diffusion coefficient multiplied by the noise, provided that the bad terms which involve the V norm both in the growth and Lipschitz condition are small enough, then one has a unique solution which is as usual in the set of continuous functions taking value in H and square integral functions taking value in V, and furthermore that some a priori estimate is going to hold. Very soon I'm going to have to change to put some here kind of shift my Wiener process by some random element of its reproducing kernel Hilbert space, and some estimates like that will have to be proven uniformly on some balls. All right, now down below I have quoted a few people who have proven well-posedness and a priori estimates in this framework of Navier-Stokes equation in 2D with random perturbation, with multiplicative random perturbation, shell models with additive noise, and so on and so forth. All right, and I'm sure I've forgotten many things, many people, and I apologize for those which are not quoted in here. All right, now, as I told you a moment ago, the problem is what's going on when the viscosity goes to 0. And let me first deal with some general results. And as you might expect, because the viscosity, if I go back here, this viscosity is in front of the Stokes operator or some kind of Laplace operator, which is very smoothing. If you lose the viscosity, then you're in trouble. You're in trouble, which means that you are going to have to reinforce the assumptions you make on the diffusion coefficient, on the initial condition, and you are going to be not get as good results. All right, so let me first give a short reminder, but because there I can save time, Professor Japchik in his talk gave a very nice introduction to large deviation principles. So I'm here dealing with a Gaussian noise. So the Schilder theorem tells me that this family of trajectories satisfies in this space a large deviation principle with a rate function which in terms of Gaussian processes can be thought of as energy. You are taking the derivative of the trajectory, integrating it with respect to time. And okay, this is 1/2 coefficient which pops out, but it's not really important. And okay, this has this explicit formulation provided that you are in more or less the reproducing kernel Hilbert space, except that this notation means upper integrals of something which is a reproducing kernel Hilbert space, provided that you deal with a compact Hilbert-Schmidt embedding. So it's a bit complicated to formulate, but nothing really bad about it. And now let's go back to our equation, and we would like to be able to deduce a large deviation principle when now the viscosity goes to 0, more or less related to this Schilder theorem. But the problem is that large deviations here, as you can see, require that the noise be shrinked, be multiplied by some small coefficient. Now, if I require that my viscosity goes to 0, I do have to impose that the noise perturbation is going to 0 as well. And here there is a scaling between the way my noise is being shrinked and the way my viscosity is going to 0. Maybe because of L2 isometries, the right way to shrink here the noise is to multiply it by the root of the viscosity if I want to remain in this framework of Van-Silfen large deviations. All right. So, of course, a simple-minded idea is look at the map which maps the noise to the solution and hope for the best. If this map turned out to be continuous, then I would be in business, everything would be trivial, because there is a very general theorem about which is called the contraction principle, which tells you that whenever you have some continuous map and a large deviation to start with, then the byproduct, the push forward, is going to be satisfying large deviation as well. And this large deviation is described in a kind of optimization way. You just look at the infimum of all the energy you are spending in order to achieve this trajectory, and to minimize over this possible energy over all the passes, which is going to give you the trajectory. The problem is that it would be swell if I had an additive noise, but in the case of multiplicative noise, forget it, it's not continuous. And therefore, we have to kind of cheat with the lack of continuity. And the price to pay, as I told you now, lots of price will have to be paid. The basic price to pay will be already to make stronger assumption on my diffusion coefficient. Now I no longer may afford to have the gradient in my diffusion coefficient, so I need here to have upper bounds which are solely in terms of the H norm, no V norm anymore. Well, we'll see in a moment that it's yes and no, because some trace of the gradient can be kept. All right, so that's not so bad. But what's worse is that now we are letting the viscosity coefficient go to 0, and we'll have to pay the price for initial condition, which is in here. And we'll have also to pay the price for the kind of topology we are going to be able to use. And this is closely related to what Professor Zapchik mentioned yesterday. Namely, again, he had some A operator which was not smoothing that much, and he had the price to pay, which was the topology for which the large deviation principle could be stated. So we'll have exactly to face the same problems. All right, so eventually we'll have to deal with the inviscid equation. So here, what the thing which has been going on is that I've replaced root of nu times dwt by some integral with respect to the reproducing kernel Hilbert space, a deterministic one. And beside that, everything is the same, except that here I forgot to repeat U0H, so that's just B U0H, B U0H. And as you can notice here, I have no operator anymore, no Stokes operator anymore, in the case, for example, of that deviation of Navier-Stokes equation. All right, and let me first now look at the toy model for which B is not as nasty, and I can hope to have kind of better looking large deviation principle, even though it doesn't have much of a physical meaning. All right, so now here it looks frightening, right? Now I have some interpolation space which is going to pop out. As I told you, I'll have script H, but depending on some extra conditions I'm going to have to impose on my diffusion coefficient, I can have alpha range from 0 to 1/4. 1/4 is a threshold. I cannot go beyond 1/4, at least with my technique. And so the alpha norm is just the H norm of A to the alpha u, and our script H is the previous interpolation space I mentioned. All right, and as I told you, I can put back some of the gradient in here. So in fact, in the evolution equation, as long as I have viscosity, I can have my diffusion coefficient which does not contain any trace of the gradient, plus something small containing some gradient, which I denote by sigma bar. So sigma is, as previously, only only upper estimated in terms of the H norm, force for growth condition and Lipschitz condition. While, as you can see, sigma bar nu can involve, well, for the growth condition for our technique, we can really have exactly what we would like, namely the V norm, and for the Lipschitz condition, we have the V norm. But because we are going to have to deal with the V norm of the solution, we also have to push forward regularity, not regularity, but control of the diffusion coefficient by A to the 1/2. So here you see there is some upper bound, which gives you the Hilbert-Schmidt norm of sigma of u in terms of the H norm of u. And here we have pushed a sigma by A to the 1/2, and here, of course, we have pushed the H norm to the V norm. And all the assumptions are more or less of that kind. In the right column, more or less everything has been pushed forward by A to the 1/2, as far as hypotheses are concerned. And now I have some extra condition in here, because I'm going to be able to state the large deviation principle, provided that I'm putting some extra condition. Of course, if alpha is 0, this is no extra condition. I have identity, and this is just this Lipschitz condition, right? While here, if I take alpha strictly larger than 0, because I only can go up to 1/4, I have to impose some extra condition. All right. Now, once this strengthening of hypothesis has been done, suppose that we have taken, so now we are in the toy model. That means that we have these sequences of complex numbers and A and B, which appear in the description of the bilinear term. Suppose that the choice of A, B, and mu has been done in such a way that here you know that B of u, AU is equal to 0 for V in V. And suppose that both diffusion coefficients sigma and sigma bar satisfy the previous conditions C and C alpha for some alpha in between 0 and 1/4, and go back to our perturbed equation where mu is the viscosity and the noise is being shrunk by the root of mu. Then we can prove a large deviation principle. Well, the solution, in fact, because I've improved here the regularity of the initial condition, I suppose that my initial condition is in V. My solution lives in C of 0t in V, included an intersection with L2, 0t in domain of A. But the problem is that, unfortunately, I can only prove a large deviation principle in the continuous function taking value in H alpha, not more than that. That means that at most, I can go to the domain of A to the 1/4. And beside that, I mean, the rate function is described exactly in the way you would describe it if the map were continuous. The map I mentioned a moment ago and told you if the noise is additive, this map is continuous, and then you can use the contraction principle, despite the fact that we have here some non-constant coefficient. The rate function is exactly the same, namely, again, minimizing energy for among all the trajectories which are going to give us, so the H term, so that means the element of the reproducing kernel Hilbert space of the noise W, which drives the solution of this inviscid equation and gives you the trajectory. All right, let me quote some similar result by Mariani in a completely different framework. He obtained some result in a framework of evolution equation for conservation laws. And again, he had some operator which he would multiply by a small coefficient, and he would multiply the noise by some power of this small coefficient. And then he had some kind of scales of power for which different phenomenon would appear. Okay, now some comments about large deviations. Well, again, here I can save time because Professor Zapczyk told us already what large deviation means. It's some kind of exponential decay, except that here I've described things in terms of open and closed subsets instead of taking interior enclosure as we did yesterday. The rate function should be a good rate function if I want my technique to appear, which means that to work, which means that the level sets ought to be compact subsets. And what else is and on the stronger assumption I had to make were made in such a way that I would be sure that the solution to the inviscid equation would exist. That's kind of easy, but would be unique, which is a bit more tricky. All right. So that's the statement we can have, the previous statement we can have in the case of the toy model of shell models of turbulence. Now, let's move to, so to speak, the real thing, namely the Navier-Stokes equation. And here again, we'll have to face a problem. So the problem is what's going on when nu is equal to 0. So what's going on in the inviscid case? So the inviscid case was studied in some deterministic frameworks by several people, and again, I'm sure that I'm missing quite a few. And it was also studied in a random setting by Hakim Abessai, Krishna Tejat, I think Franco Flandoli as well. I'm sorry, maybe I forgot your name. I apologize for that. Okay, so now we have some deterministic control. It eventually will be a random, might be a random control as well. And we will impose that this control remains in some ball of the reproducing kernel Hilbert space. That means that the upper integral from 0 to infinity of the square of the H0 norm be less than or equal to some constant. And again, I will have to strengthen assumptions. I already have paid the price for in the case of shell models, and I'll have to pay the price in this case as well. So here, once more, I'm forgetting about the V norm, and here I impose something about some control. I'm sorry, this is a discrepancy. It's curl and curl. I forgot to change this one. So here, the square norm of the curl of sigma should be upper estimated in terms of the square of the H norm of the curl of U as well. So this is nice to have existence of the solution to the inviscid equation, and more or less the idea will be, as was done in the work by Preshnak and Pejat, where they had some stochastic control to put some small viscosity coefficient, get existence of the solution, let the viscosity get a priori estimates which do not depend on the viscosity coefficient, let the viscosity coefficient go to 0, and you're in business. But the problem is that you don't have uniqueness. And I would like my rate function to be stated in terms of the unique solution to the inviscid equation. So that means that I'm not that well off. Nevertheless, I'm not too badly off, because if I take the supremum of the V norm, because here again I have supposed that my initial condition is more regular, and if I remain in some ball of my reproducing kernel Hilbert space, this is upper estimated in terms of the V norm of my initial condition and some constant which only depend on the length of the time interval and the radius of the ball. All right. Now, the problem again is that I don't have uniqueness as a result. And because of that, if I want to have a uniqueness result, I will have to go in non-Hilbert Sobolev spaces. So let me denote by norm Q the usual LQ norm, and KQ norm of U, which will be the usual Sobolev norm. And well, I just here gave some results which I'm going to use in the proof, but I'm not really going to go in the proof deeply. But because of the choice we have in dimension 2, we know that H12 is included in LQ on one hand. What's more important in here is that if Q is strictly larger than 2, H1Q is included in L infinity of D. So to start with, I guess I should have told you some information about the domain. I take it, let's say, regular enough. So regular enough, definitely, for example, the cone condition ought to be satisfied in order to have Sobolev embedding, and I should have some nice surface integral to start with. All right, and the bilinear operator can be extended from H1Q cross H1Q for any kind of Q larger than 2, of course, strictly less than infinity, and it's going to take value into some negative Sobolev space. Enjoy the same antisymmetry property, and on top of that, the curl of B in a kind of a duality relation with more or less, intuitively speaking, the Q minus 1 power of the curl, which is what's going down for the adjoint operator. If you look, not the adjoint operator, but if you look at LQ, the complex conjugate will be Q over Q to the minus 1, and it's kind of natural to have something which appears to the Q to the minus 1 power. And you have some upper estimate of the LQ norm of B of U in terms of the product of the H1Q norms of the items U and B. And this inequality holds provided that Q is larger than 2, and that the trouble, that's why we have to go outside of the framework of Hilbert Sobolev spaces. Now, the problem is that once you have done that, well, trouble begins in a way, because the proof, which I did not mention at all, was based on the E2 formula. And the E2 formula, that's fine if you have in a Hilbert setting, because then everything is nice and easy. So that means that here we'll have to go into finding some E2 formula which is going to be able to deal with some non-Hilbert Sobolev space norm, and this will require some more involved stochastic integral. So here let me remind you about stochastic, remind you or learn you, I don't know, because I must admit that I learned that for this paper, about stochastic integral for radonifying operators. So suppose that Y is a Banach space, and you have some operator from H0 to Y. It's going to be said radonifying if more or less it behaves as if it were Hilbert-Schmidt. That means that you take some orthonormal basis of H0, which is denoted by EK, and some sequence of independent standard Gaussian random variables, and you look at this series. Except that you are multiplying your random variables by the image, the push forward of EK by this operator. And you would like this to converge in L2 of omega and y. And if that so happens, then denote the radonifying norm, square of the radonifying norm of this K operator as the expected value of the random variable you are going to obtain, the y norm of this random variable. All right, and now we have to be able to pursue with stochastic integrals. And the problem is that the stochastic integrals should be extended from step functions to any reasonable square integrable function. And this cannot be done in any old Banach space, but fortunately enough for us, it can be done in the WKQ, the Sobolev spaces, provided that Q is larger than 2. And once we know that the stochastic integral can be defined, of course, many tools should be obtained. On one hand, a basic inequality, which is a Burkholder-Davis-Gandy inequality, which tells you that the supremum of the piece moment of some stochastic integral, and here I've taken the Sobolev norm, should be upper estimated by, well, more or less what you expect, namely the p over 2's power of the integral of the norm. And here, instead of having the Hilbert-Schmidt norm, you have the square of this radonifying norm. Okay, so these results can be found in a few papers that Weiler, Neidhart, Przesniak, Peshat, and the latest one, Zhyslav-Tormi, is by Andrejat, which has some kind of a neat formulation of this Burkholder-Davis-Gandy inequality. And the second, of course, very basic tool, that's the E2 formula. So here, again, it looks a bit frightening because you have this extra term. So let me give you some notation. So I have this radonifying operator, and let me denote by gamma q the distribution of these random variables, which I know exists by the very definition of my radonifying operator. And now I have some bilinear continuous map from y cross y to z. More or less, this will be the second derivative, which is in here, in the future. And you have some. So now, for the time being, I will only be interested in the particular case that y is equal to LQ, and my function, the only function I'm going to be interested with, will be the q spar of the p spar, of the q's norm for any p larger than q, larger than or equal to 2. So you get more or less what you expect. That means that here, okay, because maybe for the time being, suppose that p is equal to q, this term vanishes, and again think about the case q is 2. P is equal to q is equal to 2. Then you exactly recover what you expect, namely the scalar product between the drift coefficient and your process. Same thing here, except that you have the scalar product between your drift coefficient and your stochastic term. And here 1/2, and here you would have the trace of the Hilbert-Schmidt operator. Well, here, everything has to be adjusted. That means that because you no longer have q is 2, you have here this guy, which replaces the inner product between b and psi. It has to be psi every time has to be multiplied by the q minus 2's norm of the absolute value. And because now I've taken p larger than q, again some power of the remaining power of the q's norm should appear. And this is very general. No, not very general. I'm sorry. This is I'm doing that for a very peculiar function psi, the only one which I'm really interested in. And of course, this guy, which is here described in terms of an integral with respect to this distribution of this linear term, is not very appealing. But fortunately for me, nice people proved that you can some upper estimate of this class, of this trace, by something which is exactly what you expect and you can deal with. So you are more or less in business as if you were in a Hilbert space setting. All right. So now price to pay to get uniqueness. So again, I will have to obtain sufficient condition to get uniqueness of the control Euler equation. Control Euler equation means that I'm replacing the noise by some element of its reproducing kernel Hilbert space. And now I'm dealing with some q strictly larger than 2. And I'm assuming that the curl of sigma should be well behaved, except that this time it's going to take values in the set of radonifying operators in LQ. More or less, sigma is taking value in H1Q, but since I'm taking the curl, I'm already taking some derivative, and I only have to deal with LQ norm. Again, I have some control which ought to be given of this curl in terms of the Q norms of U and the Q norms of the curl of U, and some Lipschitz control, which more or less is what you expect. You can give some trace here of the Q norm, but of course the nasty part is these Q norms of the curls. And the other big price we have to pay is that we have to impose that the initial condition be more regular. That was kind of expected. That means you have to take it in V. But on top of that, you have to suppose that the curl of your initial condition belongs to infinity of V. And in that case, exactly as if I had a deterministic, standard deterministic, nicely behaved F term in the right-hand side, I can have well-posedness and well-posedness in C of 0t and H1Q for Q larger than 2, and a nice control which is given to me in terms again of the length of the time interval, the radius of the ball where I'm taking my control, and of course the norm of the H1Q norm of my initial condition. So here there is discrepancy between hypotheses. I have to suppose that the curl is in an infinity, but here only the H1Q norm is appearing. And now let's go back to the random equation where I will have this W term multiplied by nu. And once more, I can get uniform bounds uniformly with respect to my viscosity of similar piece moments of the H1Q norm in terms of exactly the same. All right, now maybe you wonder whether what I've described as sigma does exist. Well, the answer is fortunately yes, it does exist. You can have what's called Nemetsky's operators, which more or less are those which were described, I think, in Professor Ju's talk. Since Q to the 1/2 is Hilbert-Schmidt from H to H, because I should not forget, well, I have now two sets of hypotheses. On one hand, my noise ought to be Hilbert-Schmidt or to have trace class in H, but so that means that I have some Hilbert-Schmidt operator from H to H, and I have some integral kernel. And in Preshniak and Pejat paper, there are two sets of examples which tell you more or less that when you describe everything in terms of moments or WQ norm of this kernel, and you just describe your diffusion operator as being given to you by multiplying your functions by some nice guys, well, provided that they are really nice guys and there is some balance between the regularity on the kernel and the regularity of the function you are multiplying, everything is fine. So the set of hypotheses is going to be satisfied. And here I have a slightly different set of hypotheses and a slightly different set of constraints on this multiplicative factor. But in both cases, I know that my sigma operator is going to satisfy my assumptions. All right. And now the result we can prove is the following. And very soon, I'm going to give you some work in progress and some hope I have to improve this result. But for the time being, it's not extremely a strong result, as you will see. So to start with, I have to take an initial condition which is in V, so that the curl is in L infinity. I have to strengthen the hypothesis on the diffusion coefficient the way I told you. And then I know that my stochastic differential equation, my evolution equation, will have a unique solution in a better space, because in fact here I could replace LQ by H1Q. But unfortunately, again, because in the limit I have cancelled this term, I can only for the moment prove a large deviation principle in LQ. And once more, the large deviation principle is the rate function is described the way you expect. Again, that's a minimization of energy among all the trajectories which matches the one you want to. with the driving force here, the energy being given by this driving term, which is here driving the inviscid control equation. All right, so let me mention several directions where I think some improvement can be done with respect to what I've just stated. That's work in progress with Hakima. On one hand, the diffusion coefficient may depend upon time. So then, as long as I do not tell you how I prove things, you don't see how, what kind of assumptions I have to make. But if you start into the technique and here want to see how things are proven, then one might have to make different assumptions on the time regularity of sigma. So with the technique we have, we know how to deal with, provided that the time regularity of our diffusion coefficient is Hölder. Very small, positive, but some Hölder regularity, because this depends on the technique we have used. So that's what we've done in shell models. And we can exactly provide, with the same technique, we can deal with the Navier-Stokes equation. But Ren and Zhang, but it's not, I don't think it's you, I think it's another one, that's right, proved of course, these two people, Ren and Zhang, they dealt with an evolution equation which was in a nice Lipschitz condition. It didn't have this nasty B term, but they had a nice technique which would allow not to use time regularity, but which was based in some kind of, again, time control, but in C of 0t and V prime. And thanks to this nice control they could obtain, they could afford not to impose time regularity on the diffusion coefficient. And another approach by Liu, which he did in a general framework of stochastic evolution equation with monotonicity properties. Again, he didn't want to impose time regularity on the diffusion coefficient, but he had to impose another set of assumptions which were some kind of approximation properties of the diffusion coefficient. So that might work as well in our context. I don't know yet. I think this first approach, I'm pretty confident that it's going to work in our context because we have a bounded domain. Second direction, things ought to be improved. We should be able to do as in the shell model, namely allow some part of the gradient, provided that in our viscid equation, when the viscosity is strictly positive and we have some stochastic evolution equation, we multiply it by the root of the diffusion coefficient. And of course, the best thing, the most appealing thing to do in our program will be to try to improve the set where the trajectories is living, not only get LQ, but some at least positive, so we'll have space, some fractional differential with Q larger than 2. Again, I think that this can be done and this can be done, and this I'm pretty confident. For that approach, I don't know yet because I've not really thought a great deal about it. Okay. I have at least 10 minutes, I think, because I started late. 10 minutes, okay. So I think I will not need more than that. Don't worry. I'll try to give you some ideas about the proof. But I think Marta in the next talk is going to give you more information, more basic information about the proof and the way, the approach of this quick convergence. All right, so let's go back to this map, which goes from the noise to the solution. And let's denote by G0 the map which is going on in the case of the limit equation where we no longer have a random term. So as I told you, the map G nu is not continuous, and a standard approach by Friendlin and Wenzel, was kind of show that provided you throw away an exponentially null set, you are continuous. And throwing away this null set, exponentially null set, that's exactly what large deviation principles are about, because you deal with exponentially small sets. All right, so this was, of course, studied a lot in the framework of finite dimensional equations, and it was also used in the setting of infinite dimensional equation, but in many cases, I know of at least, the solution equation were formulated in terms of the Green function. These were mild formulations. right? And so here again I've quoted a few people who have dealt with this method for infinite dimensional setting. But it's a very heavy method, and I don't want in my setting to use a green function. So a more recent approach, which is called the weak convergence approach, which is very much related with the talk of Professor Zabchik yesterday, is much more efficient in this infinite dimensional setting. It was introduced by Dupuis and Ellis, and it's based exactly as what Professor Zabchik mentioned yesterday on the equivalence between large deviation principle and the Laplace principle. That means that instead of proving directly a large deviation principle, you prove that whenever you have some nice continuous and bounded function, some expected value is going to converge. Okay, so then it was, and Marta again is going to explain you more about this issue. Boudiraja and Dupuis extended this method to infinite dimensional mild solution, and then for small perturbations, where it's a different approach, because in small perturbation the operator is fixed and you only let the noise go to 0, while here we both multiply the operator by a constant going to 0 and the noise. It was used again by several people, and I'm sure again I'm forgetting some people, and I apologize for that. So what's the crux of the matter? The crux of the matter is again going to look at a ball of the reproducing kernel Hilbert space. So here this is a nice deterministic ball, but you see right away that I'm going to take random elements of that ball, and I require that these random elements almost surely belong to the ball, and of course because I want to do stochastic analysis, that these random elements are nicely measurable, so they're predictable elements. And now I am going to, in the right hand side, more or less intuitively speaking, I'm going to translate my Brownian motion by h nu divided by root over epsilon. That means I'm going to use some kind of Gersanov transformation. So once I know I have well-posedness, the Gersanov transformation right away gives me well-posedness as well. No problem about that. The problem is controlling the norm. And as we will see in a moment, it's absolutely crucial to be able to control the norm of this stochastic controlled equation. Stochastic because here my stochastic integral is remaining, and controlled because here I've shifted my Brownian motion by some element of its reproducing kernel Hilbert space. All right? So let me denote by h nu, u nu, h nu, the corresponding solution with these two items. And here I have some h nu, which again is going to depend on my small parameter, not just one fixed h, but a family of those h's. And two things have to be checked. The first thing is that whenever I take a family h nu and some limit point h, but this limit point is in a very weak sense. That means that as nu goes to 0, I will impose that my controls converge in distribution to h. With this convergence in distribution, that's harmless, because change space, you're just dealing with Low's distributions, and you can get almost sure convergence. But the bad side, the bad news is here. The bad news is this convergence only holds for the weak topology of Sn. So it's fairly weak sequence of a fairly weak convergence. And then you have to show that whenever you look at this family of solutions to your stochastic controlled equation, it's going to converge in distribution again, but in distribution because h in application might be deterministic. That's the same as in probability. So it should converge in distribution in the space where you want to prove your large deviation principle. So that's the most difficult thing to obtain. And then some result of that flavor, but kind of simpler, is proving a compactness of the family of images if you remain in a ball of your random reproducing kernel Hilbert space. And again, this compactness can be dealt with in terms of weak compactness and sequences. So that means that more or less the step 2, that's easier way than step 1. So if you know how to do step 1, you're in business. All right? Now, what are the key points of the proof? So let me go back to the toy model, for which things are kind of easier to explain. So the absolutely crucial point is here, is that you want that provided that, okay, here I've put back the framework of shell models, namely that these constraints which ensure me that everything will be nice, I'm remaining in a ball, but now I have random elements. I have some random elements of my ball of the reproducing kernel Hilbert space, and I'm looking now at the solution to my stochastic control problem. I'm supposing that in the shell model framework, zeta is just in V, that's good enough. And then this will have a unique solution, and of course, because I've increased the regularity of my initial condition, I have better behavior of my solution. But what's very important is that there is a constant, some kind of absolute constant, which only depends upon the radius of the ball and the time length of my interval, such that whenever my viscosity is smaller than some threshold, nu naught, this threshold comes from the fact that here, I should have put sigma nu, I'm sorry here, because I can here afford to have some dependency upon the gradient, in the shell model business at least. I am going to have some upper bound, which is going to be independent of my viscosity, which is very important, independent of my individual element H in the ball. And here I will have the soup of the B norm plus some trace of the norm of A. But of course, because my viscosity is going to 0, as the viscosity vanishes, gets smaller and smaller, this nice byproduct, this nice norm, is going to vanish as well. This is absolutely crucial because right away, what do we want to do? We want to prove the step 1. Namely, we'll have some family H nu of predictable elements of our stochastic elements in the ball, and we are supposing that they are going to converge to H0 in the weak topology. Chain probability space, you have weak convergence. You have almost sure convergence instead of here convergence in distribution. But the problem is that we only are dealing with a weak topology. And so our approach was to say, okay, it's weak topology. That means that whenever we integrate with respect to towards some indicator function of 0t, we have weak convergence, right? And because we have, more or less intuitively speaking, because we have some nicely behaved diffusion operator, if you fixed our diffusion operator, it's going to turn weak convergence sequences into strong convergence sequences. So weak convergence sequences is not going to be a problem. But the problem will arise in a moment. So we are going to here look at the difference between the stochastic term, the deterministic term, and we would like that the supremum of the alpha norm of this difference go to 0. Oh, okay, I guess here the square is quite foolish, right, in probability. And in order to do that, we want to deal with convergence in probability. That means that we can throw out a null set, not a null set, sorry, but a small set. And after having thrown this small set, we can prove convergence in L2, right? If we can manage to prove convergence in L2, except outside of a very small set, we're in business to prove convergence in probability. And here is the good set, that's G for good. So here is a good set where I'm going to localize everything, which is control everything. So, and of course, this set the probability of this set should not depend upon the viscosity. And that's why these uniform a priori estimates we proved in the previous slide here, this thing, were crucial in order to show that provided that the viscosity is small enough, the probability of that is close to 1. All right, so that's exactly the first step. The first step tells you that according to the a priori estimates for small viscosity, you can make sure that if you have a threshold n which goes to infinity, which is large enough, uniformly with respect to the viscosity and uniformly with respect to the elements in the ball, you will get that the probability of the complement of your God set is very small. And once you have done that, you just look at square L2 norm localized on this good set. And now the technique we used, as I said, was trying to make some discretization, some time discretization. And okay, I guess I'm running out of time, so I will not explain why one has to do some kind of thing like that. And here, of course, if you think of the Navier-Stokes equation and you want to write down something in the V norm or even in the H norm, forget it. It's not going to work. Because if you take an increment of the magic item of the Navier-Stokes equation of the B term is that B of u is equal to 0. And if you are outside of this framework, you are some trace of B which remains. And this B term is very nasty because it introduces some V norm. That means that in finite dimensional settings, for example, you could get a control which would not be integrated with respect to time. You would just get some estimates of some power of your time increments. But because of the B operator, and here we even have to deal with the V norm, which is even worse, but I mean, it's not really a problem because in our G operator, in our G localizing set here, we can get our hands on that, which is exactly what's needed to do that. Provided that you reintegrate on time, you're in business because you have nice properties of the bad norm in time. And fortunately enough, if you localize this kind of time increments, you can get something which goes to 0 as again goes to infinity. That might not be the best way to go to 0, but that's good enough for what we have in mind. And for the Navier-Stokes equation, let me just more or less give you the crux, the main step, which is again to prove these a priori estimates which are uniform in the ball whenever the viscosity looks like. And again, of course, then I have to put everything on my hands. The initial condition ought to be in V, the curl should be in L infinity, the sigma diffusion coefficient should satisfy both the Hilbert-Schmidt and the Radon-Effeng assumptions. And then I can get a uniform control with respect with some constant, which only again depends on the various exponents I've taken in here, the length of the time interval and the radius of the ball. Thank you for your attention.
Thank you. Are there any questions?
If there were no uniqueness, could you still get something about large deviations?
Yeah, we thought for a long time concerning this issue because, of course, it's at the crux of the matter. Many of the effort we have to do is because we want to have uniqueness. To be honest, Hakim, I think we can deal without uniqueness, and I'm very reluctant. So I feel much better if I have uniqueness, and I don't think we can do it without uniqueness. But okay, there is a disagreement between both of us on this issue. Yeah.
There is a variant of the 3D Navier-Stokes equation called the tamed 3D Navier-Stokes equation.
Oh, that's right. You published, yeah, I saw a recent paper.
It would be an interesting, I mean, one can prove the usual large deviations. I mean, this, as you say, we have done in the recent paper. But the question is, can you also do your thing, I mean, with viscosity in front of the Laplacian in 3D?
I just got hold of that paper too recently to tell you, and for the time being, I would like just to pursue make the improvements, I hope, in the two-dimensional setting, but of course that would be very interesting to go to the 3 dimensions. I have no feeling for that.
Because the feature of this 3D, this tamed Navier-Stokes equation in the deterministic cases, if the conjecture is true, I mean, if you can solve the clay problem, then the solution will be bounded by Haywood inequality. And then the solution of the tamed Navier-Stokes is the same as the one of the classical 3D Navier-Stokes equation. That makes it interesting. Of course, in the stochastic case, it's different, but at least in the deterministic case, you are studying the solutions, if they really exist for all times, of the original one. And therefore, I think it's a very nice toy model also for these questions.
Sure. And do you have uniqueness of your...
yes, in that case, yes, because we have a tamed term that gives us uniqueness.
Okay, all right.
And we even have in the deterministic a strong solution.
But you also feel that uniqueness is important.
Yes,
okay.
definitely.
That makes me feel better. Because I'm the one who does not want to go out of uniqueness.
But you mentioned Mariani. So his case is exactly a case where the deterministic PDE is not well posed.
Yes, I know.
He has a large deviation. So
I discussed this with him, and I do not completely understand all of his argument. But okay, by the way, he's also trying to work on the large deviation principle for inviscid Navier-Stokes equation, but it seemed that the ways we were looking at things were different enough so that we would not spoil each other's life. Yeah?
You mentioned this paper of the two Indian guys. I always forget the name.
Sridharan and Sundar.
Right. There was a. This was for the 2D Navier-Stokes. The regular.
That's a 2D Navier-Stokes
There
equation.
was a gap in that paper.
Oh yes, I know. Okay, I
Isn't
did not.
Erratum published meanwhile or corrigendum?
I don't know. We mentioned this gap to them, but
Any other question? Comment? Well, if not, thank you again.